Hello, today we're going to talk about missingness, some heuristics for when your data is missing. My name's Quinn. I'm a section lead at Lambda School. I'm just going to have a brief overview of imputation, an overview of missingness, and the three regimes, the three different ways data can be missing, and a brief study on the bias introduced when you impute missing data. I'm assuming that you know what this means. It's basically a rate of missingness. You can take the indicator matrix, and then you can take all the column sums of the indicator matrix being 1 if it's missing and 0 if the value's there. And when I divide that by the total number of observations, I get a percentage, right? So this is the missing rate of the data. I'm assuming you filled with column mean at least once, where I would say take the age column and fill all the null values with the average age, right? This is the basic imputation strategy, filling with mean. And I'm assuming some pandas syntax. So it's not really a workshop on imputation strategies. It's not really a workshop of any kind, and I'm not going to be mentioning dropping or interpolating, which are two totally different ways of dealing with missing data. We're just going to talk about some strategies that might point you toward wise experimentation. So what is imputation? Well, in statistics, imputation is the process of replacing missing data with substituted values. One of the most common substituted values is the mean. You can also do the median. Missingness is classified into three different regimes, we call them. The three different ways data can be missing, where missingness is a property of the data set, right? In one way, missingness is a feature of a function. Missingness of a feature is a function of that feature itself. A feature can predict its own missingness. Another kind is when the missingness of a feature is a function of other variables. This one's sort of complicated because there's two different ways for this case. This case breaks down into whether the other features that predict missingness are observed or whether they're unobserved. Because remember, sometimes things you can't collect data for them, but they're still considered variables. They're just unobserved variables or totally unknown variables. But both kinds are that second category. The third type is when missingness is truly random missingness. So the technical terms for these, the first, again, missingness of a feature is a function of itself. This is called MNAR, for missing not at random. The second one, when the missingness is a function of other variables, this we call MAR, or missing at random. And third, missingness of a feature is truly random, and that is MCAR, missing completely at random. So the technical terms aren't that useful. Focus on the concepts, less on the names of the concepts, right? But just, truly random and completely at random, they correspond. So how do you know which it is? In basically any case, your domain knowledge is gonna prevail over any test that you can do. Any analysis you do of your data, we'll make some suggestions and we'll see a little of that. But at the end of the day, think about your domain, talk with your domain experts, and think about how the data was collected, experiment design methodology. These are going to lead you to insights about missingness more than just raw statistical tests. So MNAR, missing not at random. Again, this is where missingness of a feature is a function of itself. The best thing you can do is domain knowledge, is data collection methodology. How much do you know about it? This could lead to some sort of commonsensical insight, as we'll see in this example. You can't prove MNAR mathematically, But there are closer to ways you can mathematically show it's not MAR and it's not MCAR. So an example of this is if I'm collecting height data, data about people's heights, and I'm doing it by having them write it on a piece of paper and drop it into a box, right? But then I put that box 9 feet off the ground. So what's this going to do? Well, it's going to systematically exclude short people from the data, right? People who can't reach up to 9 feet to drop the data in, they're going to be missing. So the missingness is going to be told by essentially the feature, the variable height itself. Missing at random is the next regime. Missingness of a feature is a function of other variables. So you imagine you find some function that takes a sequence of variables and returns the indicator matrix, the indicator vector of this particular feature. So an example is if someone's collecting movie preference data by, again, writing it down on a piece of paper, having the respondents write their rank ordering on a piece of paper and dropping it into a box, and then putting that box 9 feet off the ground. Okay, so this is going to be MAR, missing at random, because movie preference data is going to be missing based on height, right? Height is going to be the thing that predicts missingness in rank ordering because the box is 9 feet off the ground. And I stress, missing at random applies to 2 cases. It applies to the case where you magically have height data to begin with, and it applies to the case where you don't have height data. Okay, so we will still call it missing at random whether or not you have the value, the variable that predicts the missingness. So this is important, and it'll lead to 2 different strategies, 2 different things that you can do. When you don't have the variable, it just sort of helps you have an intuition for why the data is missing. It doesn't directly tell you anything that you can do. When the variable that predicts it is in your data set, then you have some more options. And we'll see that on the next slide. But first, just another thing you can do, if the predictor variables are in your data set, you should be able to discover them like this. So what you do is you take the correlation matrix of the indicator matrix. Okay, so it's the correlation matrix, the matrix of the correlation, the Pearson correlation coefficients. The indicator of the indicator matrix, the matrix that's 1 if the value is missing and 0 if the value is there. Strong correlations in this matrix, so say numbers higher than 0.75 in this matrix, that's going to suggest that you have some missing at random, totally in your data set. You can also target the indicator vector in a logistic regression. The stronger coefficients will be where MAR is. Coefficients that are particularly impactful to the model, you're going to want to suspect MAR. So what do you do? What do you do if you suspect missing at random? You should try something called multivariate imputation. Okay, multivariate imputation is an algorithm. It's a strategy. Yes, Sklearn has implemented it quite recently. It's called iterative imputer, and this is basically looking for this function. Long story short, it's inferring a function that sort of works like this. And to properly do multivariate imputation by chained equations or mice, you have to do this multiple times with some randomness and some bagging, and pick the best one. But just running iterative imputer once can still be pretty good sometimes. So yeah, you shouldn't be surprised. You shouldn't be too surprised if you suspect missing at random based on one of these tools, and you try iterative imputer and it doesn't outperform some other strategy, because sometimes it won't outperform the other strategy. But If it does perform strongest, you definitely shouldn't be surprised, because iterative imputer is performing stronger than my other imputer methods. Well, you know what? That makes sense to me because I saw the correlations in the indicator matrix, right? But you're never going to come to a place where you're not using common sense. You're never going to come to a place where you're not experimenting, and that's really important. Experiment and common sense prevail over heuristics. So missing completely at random. This is basically the last one. This is when the missingness of a feature is truly random. There's a pretty high bar. There's a pretty high burden of proof here. I really don't understand it. It's above my pay grade, frankly. It makes the most sense in the ideal condition, but in real life, it's really hard to say that there's not some hidden MAR, right? A MAR with a unknown variable, and that will appear very, very similar to true randomness in your data, but it's really not the exact same. So an example when you might run into this is, what if a goblin has set upon stealing your data strictly for his amusement and strictly because it gets on your nerves, right? That's going to be the ideal, missing completely at random case, the ideal MCAR case. And so we're going to do a brief study. We're going to simulate this case. In Python, what I did was I have a function that'll process a data frame and return another data frame. And what it'll do is it'll look at every single value, and at every value, it'll flip a coin. That's what the Bernoulli variable is doing. So the goblin flips a coin. If it comes up heads, the goblin decides to steal your data. And if it comes up tails, the goblin will leave your data be. And then, again, this is purely for his own amusement. Serves no purpose. This is going to create basically data sets that we can experiment on. We can experiment on the MCAR case. It's a little more involved to come up with experiments on the other cases, but the MCAR case we can experiment easily. So here's the study. We trained a model on the complete data. Then we train a pipeline with an imputer on it that the goblin has interfered with, on data that the goblin has interfered with. So the goblin steals a bunch of data from totally random places. We impute it, we train a pipeline just so we can compare the coefficients. So we observe the difference in coefficients between the sort of control model that's trained on complete data and the data that has imputation in it. And that difference in coefficient is going to be the bias that the imputation and missingness introduced. And I'm going to do this over several different imputation tools. So filling with mean, filling with median, iterative imputer, filling with Gaussian noise. These are all things you can try. There's a library for this I'll point you to toward the end. And the data set I'm using is Driven Data's Tanzanian water points competition. This is my results. So you can see a lot of it's concentrated around 0. So the bias isn't that bad, but the outliers are pretty severe, and even the even the whiskers are. This isn't a bias you wanna roll your nose at. A bias around 0.1 when just 10% of the data is missing completely at random, that comes in just under 0.1. And that's still enough to mess you up, because these are regularized, kind of standardized coefficients. If 30% of your data is missing, that whisker totally clears 0.1. So you're going to want to be careful. And you can see the outliers go much further. So you're going to want to be careful. If you're missing completely at random, upwards of 30%, you're really in trouble. That's definitely some serious bias. And even upwards of 10%, you really don't want to be there. So you have to be really careful when you're imputing. Missingness is going to introduce bias. It's going to happen. Some imputation methods will introduce bias differently. You know what I mean? And you just gotta find the best one. So in summary, imputation is finding values to fill in missingness with by replacement. It will introduce bias. The missingness itself introduces bias, and every imputation strategy will introduce bias. There are different ways your data can be missing. Missingness is a property of your data set. It comes in flavors. It comes in regimes. Again, there is MNAR, missing not at random, when the predictor of missingness is the feature itself. There's MAR, missing at random, where the predictor of missingness is other variables. Finally, there's MCAR, missing completely at random, when a goblin is stealing your data for his own amusement. Lastly, it appears, because I started this thinking like, I'm going to find some way to axiomatize this. Like, this has got to be well understood. I can analytically come up with strategies that totally work. There's no one really in the literature expects that to be the case. Maybe some brilliant statistician in 50 years will totally change the game, will totally change the rules. But for now, the basic consensus appears to me to be that experiment, common sense, and domain knowledge, they're always going to prevail over statistical tests. So remember, experiment, common sense, and domain knowledge. These are some of my sources. I got a lot of these ideas from a talk from SciPy in 2018 by Dylan Niederhut. You should check out that. Iris Eekhout has some amazing resources from her PhD dissertation. You can find that on her website. And there's another library in Python called Fancy Impute. And they have more strategies. They have matrix completion algorithms. They have a lot going on. And so you should check that out. Thank you.